Welcome back to Discrete Mathematics. Today we're going to take a look at planar graphs. So this is definitely a tricky concept, and the hardest part is finding a planar graph when you're just given a mess of vertices and edges. So, what is it? A graph is planar if it can be drawn without any crossing edges. So here's a nice example graph. We say, is it planar? Well, the way it's drawn now, we see crossing edges right there. We see that this A to B edge conflicts with this C to D edge. So, is it planar? Well, we can redraw this edge connected on the outside here, and we see, hey, if we redraw it, then there's no crossing edges. So yes, now this graph is planar. So that's basically what we're going to talk about. And why is it interesting? Well, don't worry, we'll get to that. So here's the thing. Which complete graphs are planar? Because we should probably know, when we take a look at complete graphs, how many we can go before things start to get a little bit impossible to draw without overlapping edges. So we know that K1, well, it's just a vertex, so of course it's planar. K2, you can't really cross edges when you only have two vertices. K3, well, if we set that up as a triangle, we don't really have any issues there, so that's good. What about K4? Well, K4 was actually just the graph that I drew before. In fact, this time I'm going to draw it a little bit different. So we can draw K4 like this. And now the edges go everywhere else. In fact, that's a very cool, nice embedding of K4. I love this one. I think it looks really cool. But that's K4. We can draw that planar. What about K5? So here's the tricky part. We can connect all the edges on the outside just fine. And then we can start connecting some vertices around. So that looks like it's good. Okay, when we move up here, we have to connect this vertex to the top two. So we'll connect this bottom vertex all the way up here to the top. So now we don't have any crossings there. But now when I want to connect these two, I have to do some crossing. So we could say that K5 is not planar, but we don't know for sure because, well, maybe we just haven't drawn the vertices right. Maybe there's a different position for the vertices to make it look a little bit nicer. And maybe it'll work. So I will tell you right away that K5 is not planar. It can't be drawn without overlapping edges. But I can't prove that to you yet. We still need some information in order to prove it. Because you can't just draw a bunch of graphs and say, I can't do it, therefore it's not planar. Because it could be. It could still be planar. Maybe nobody in the world has thought of a nice way to draw it. So we have a theorem that will cover this and prove that it is not planar. But for now, let's go on to bipartite graphs. So, find a complete bipartite graph that is not planar. Okay. So here's the thing. If we have K2 and any number of vertices, so let's say we have this, so that's 2 on the left, and then we have some ridiculous amount of vertices, and then we have, of course, this is connected to all of them. Well, before we connect the second vertex, what we could do instead is just move it to the right side here, because that's probably better, right? So that way when we connect all these, we don't get any overlapping edges. So K2 with anything is going to be planar. Similarly, K1 with anything will be planar because we'll just be missing the right side. So we should probably start with K3 and start going through the numbers. So we know that K3 in anything is okay because that's the same, K3 in 1 is okay because K13 is okay. We know K32 is going to be okay because that's the same thing as essentially K23, which we know is possible thanks to this lovely graph. So the first possible one that could be not planar is K33. So let's try to draw it planar. And I'm sure we won't have any difficulties with this. It's only a total of 9 edges, so let's go. Okay. We'll connect this first one to these 3. This second one will connect with light green. We're going to have to do some wraparound to get to this one up here. We're going to have to do some wraparound to get to this one, and then we can connect it straight here. Okay, so this bottom one, we can clearly connect this bottom node to that bottom node. We can do some looping to get to this one, and oh no, oh, we were so close. We were so close to getting this right. But unfortunately, we have to do some jumps in order to get to the last node. So once again, I'm going to tell you that K33 is not planar. We don't have the theorem yet to prove it, but we will. Don't worry. That'll be next video. So, we've now found 2 non-planar graphs. Which leads us to Kuratowski's theorem. Now, Kuratowski, very, very sexy mathematician, did some very beautiful things. Most notably, in a Discrete Math 2 course, you're going to discover the Kuratowski theorem. So a graph is not going to be planar if there's a subgraph of K5 or K33 in it. And we introduce this new word, homomorphic, if it contains a subgraph that is homomorphic to K5 or K33. What is that? Well, homomorphic, 1, it can be isomorphic. So homomorphic contains isomorphisms. So if it's the same graph as K5 or K33, then clearly it's non-planar. But if we can take a graph and we can say, let's take K55 and let's start subdividing it. So that means we take an edge. So for instance, let's look at G here. Let's look at G and H. So the difference between G and H is that, I'm trying to make this nice. So the difference between G and H is that we have this extra vertex W between A and C. So what we can do is we can subdivide G by adding in an extra edge between A and C. So we subdivide the edge A and C into AWAC. So it's kind of like saying, okay, we have an edge that goes from X to Y, and we split that up into 2 edges, XZ and ZY. So that is what subdivision is. You just take an edge, you take a left side, a right side, or a first part, a second part, and you split them up into 2 separate parts that are connected at some similar node. So we can say now that H is homomorphic to G. Let's take a look at I here. Well, here's the thing. We can't get I from H because H has this W here that, well, we can't subdivide H to get to I. Because we got the W and H, the I does not have the W, it has the X and the Y. But what we can do is we can take a look at our original graph G and say, okay, what we can do is we can put an edge between A and B, we'll call that X. We put an edge between C and D, so we subdivide C and D and put Y, and now I is homomorphic to G. So even at this base here, let's take a look at the base of G without any subdivisions. H is homomorphic to G because we can subdivide G to get H. I is homomorphic to G because we can subdivide AB and CD to get to I. So if we can do some subdivisions on K5 or K33 to get the original graph that we're dealing with, then it's not going to be planar. So here's a couple examples. Is this graph planar? And I'm going to put this right after the note I said about K5 and K33 just to mess with you, because this graph is actually planar. And you're saying, hold on a second, this looks like a mess. But what did I tell you? What did I tell you about the good old K2M graphs? Well, this isn't quite K to M, but it's close. Because the only difference is, if we say remove these lines right here, then we're good. It looks like something we're used to. So let's reconnect them, and we're going to put B on the other side here. So what we're going to get, I'm not going to label these nodes. So we have the W, X, Y, and Z connected. I am going to label A though. I am going to label B. So we can get this nice graph again. So when we put B down here, we're going to get this connection. But we still have this line here to deal with. So what do we do about this line? Well, we can just connect it on the outside. And there you go. There's a planar representation of this graph on the left. Okay, so tricks are over. Here's another graph. Is this graph planar? Is it not planar? So this is a very, very tricky process, and it is challenging. It is very challenging to go through the iterations. So fortunately, I have a nice piece here that can erase and undo and draw things and make it look not messy. But if you're doing this on paper, it's going to look terrible, okay? I'm letting you know, when you do these activities to figure out if a graph is not planar, it is going to look awful on your piece of paper. So you're going to have to draw the graph a few times, do it. I'm blessed with technology, and I'm also blessed with knowing the answer, so it's going to speed it up quite a bit. So let's do it, then I'll give you some tips on how you can do it yourself. So this is a messy graph, right? Right, okay, so we want to find a K5 or K3 embedding. So here's what I do. I take a look at all the vertices here, and I kind of just write their degree above them. So I can take a look here. We got this 5 here, we have a 5 on C, this A is a 2, this D right here is a 4. Okay, this F is 1, 2, 3, 4, 5. It looks a lot more than 5. 1, 2, 3, 4, 5. Okay, that's a 6. This G is a 2. This H is a 4. Okay, and okay, this I, of course, is a 2. So what I don't see here are any 3s. So we're not going to look for a K3 graph. But what I do see are some 5s. I see a 6. So what we should do is, well, we should try to convert some of these degrees into, or some of these vertices into 5s, or see what we can do to eliminate them. And I take a look specifically at this E here. It only has degree 2, and we're looking for an embedding of K5. So here's what we're going to do. I'm going to draw the K5 graph. I'm going to draw nice and big, these giant circles. And what do I see here? I see that B has degree 5, C has degree 5, F has degree 6, we'll put that there, and H and D have degree 4, so why don't we put them there too, since these are our big candidates for what could be in this graph. So let's put in the lines that we know. Okay, B goes to C, B goes to D, B goes to F, but does B go to H? So that's the question. Does B go to H? Well, not really. It doesn't look like it goes to H. So, we know what it does though. It goes to A, and then it goes to H. So we could do this here. Let's draw B to H, and then we'll insert an A in there. Okay. So our B's connect to C, H, D, and F. Okay. Let's take a look at C next. Okay, C, does C go to D? Yeah, C goes to D. C goes directly to D. Does C go to H? Yeah, C goes to H. What about C goes to F? Well, it doesn't go directly to F. In fact, it goes to F in two different ways. It goes from C to I, and then I to F. So let's do that here. Okay. One way it goes from C to I and I to F. And then it also goes from C to G and then to F. So there's two ways for C to get to F. Okay. And that looks as if we've covered all bases for C. So C goes to B, F, D, and H. Let's take a look at H now. Does H go to D? Yes, H goes directly to D, as shown on the graph. But does H go to F? Yeah, H goes directly to F. Okay, that's good. That's covered. So here's the question, the final question. Does D go to F? Yes, it does. Okay, cool. What do we have here? Well, it looks like we have a homomorphism of K5. It looks like K5. We have an extra edge, but we have to make sure that this edge splitting, or this subdivision, contains all the vertices. So what are we missing? We're missing this vertex here, E. We don't have E in our K5 embedding, so we go from B to E to F. So what we can do is we can say, okay, let's put that in there, and suddenly now, there we go. We have a subdivision of K5 that looks like our original graph. We just redrew it. And we know that K5 is not planar, therefore this graph here should be not planar. So that's sort of one way of doing it, taking K5 and then drawing all the edges, picking candidates through guessing, and that's one way. Here's another way. So let's erase a bunch of these circles I have here, and let's box that in. So that's our solution. Here's another way of doing this. We're looking specifically for K5 in this. We're not looking at K3 because there's no degrees that are close to 3. So what we're going to do is we're just going to erase the vertices. So we see this 2 here, and 2 isn't anywhere close to 5. So we're just going to delete it. We're going to just connect the lines here. This A isn't really close, so we'll just connect this line. I will keep the letters there though, so that way we know that there used to be a vertex there. This G is pretty crappy too, so let's just get rid of that. And same with this I. This I isn't really doing us any good here. So what do we have now? Well, now we have a graph with 5 vertices. Okay, so that's kind of what we want, right? Now, do all of these have degree 5? Do they connect to every graph, to every other point? Well, we know that in K5, each vertex connects with 4 others. So the degrees must actually be 4. But here's an issue. This B here has degree 5, but what we can do is we can say, well, B actually goes to F twice. So we can pretend this edge doesn't exist, and we can say, okay, now that has degree 4. What about C here? Well, C goes to F twice. So we can cut out this one edge here, and we can say, okay, now it actually only goes to 4 different vertices. This H goes to B, C, D, and F, so that's good. It only goes to 4 different vertices. This D only goes to 4 different vertices. And this F here, well, we cut off a double edge to C, we cut off a double edge to B, so this last degree here is 4. So we now have 5 vertices of degree 4, so we should have a K5 embedding. So again, this is tricky. And then when you redraw this, of course, you just put back in the vertices, and you'll get an embedding that looks just like what we have on the right here. So this is tricky. This is very difficult to do, and it's going to be difficult every time you do it to find this. It's going to be hard to search. The best way to get good at this is to find graphs online and to practice, because there's no easy way of finding these. If there was, there would be a page in an introductory textbook saying, here's how you find a non-planar embedding, or a K5 embedding, or a K33 embedding. It's not easy. You got to be creative. You're gonna have to try a lot. If you have an exam and it says, is the graph planar? That one question, if it's not worth many points, it's probably best to take a guess and skip it and then come back to it if you have time, because it's going to take a while unless you can immediately see why it's planar or non-planar. It's difficult, straight up. So if you have difficulties with this, you can leave some comments below, ask questions, and I'll get back to you, or other people will get back to you. And if you want to check out more content, TrevTutor.com. There's also reddit.com/r/TrevTutor for a nice community there of questions where anybody can answer and anybody can post. So have a great day, and hopefully this stuff wasn't that bad.